So heat treatment of steels, there are various types of heat treatments: hardening, normalizing, annealing, then surface heat treatments. So the purpose of heat treatments is varies. So hardening is one of the heat treatment where hardness and tensile strength of a steel can be increased. Whereas normalizing and annealing, these are the heat treatments which are widely used to reduce the hardness and to improve the ductility and toughness. So tempering is also one of the kind of heat treatment generally which is carried out after hardening treatment, because after hardening you get high hardness and high tensile strength. We do not want such a high hardness sample or high hardness component into the application. So generally we reduce the hardness by tempering. So again, the purpose of tempering is not to improve the hardness but to improve ductility and toughness. Then regarding the surface heat treatments, for example, nitriding, cyaniding, carbonitriding, carburizing. So we'll change the chemistry of the surface of a steel sample by addition of certain heat treatments. So we'll change the chemical composition of the surface at the surface level. So these are the chemical heat treatments, and by doing that you will get the good hardness, because low carbon steel sample shows very poor hardness values. So we generally modify the steel or surface composition of a steel by addition of carbon elements. So that is surface heat treatments, that is chemical heat treatments. Then we will improve the hardness of a steels, that is surface hardness of a steel, by certain heat treatment, flame hardening, induction hardening. So hardness at the surface increases and hardness at the core remains same. So core remains ductile and surface becomes very hard. So in that case, you can improve wear and tear properties of the steel sample. So generally these kinds of heat treatments are widely used in case of gear applications. So heat treatment types are different. So we'll start discussion of different types of heat treatment in this particular module. But let us start the discussion by using the simple understanding that let us assume that we have AISI means American Iron and Steel Institute and SAE means Society of Automobile Engineers. So these are the designations which are widely used to designate the steel samples. 1018 is one of the AISI grade. Then AISI 1045 and AISI 1095. You can consider here, you can find out. So carbon percentage present here is maximum 0.18 percentage. In case of 1045, we have 0.45% carbon, and in case of 1095, around 0.95 percentage carbon. Now, in every heat treatment, particularly in case of hardening, the first step is to heat it up to the parent phase. So the parent phase in heat treatment procedure is the Austenite phase. So let us heat all the samples up to austenitic range. As we know, according to the iron carbon phase diagram, we need to heat all the steel samples above upper critical temperature. So above upper critical temperature means the upper critical temperature is a line above which we do not have ferrite. We have all the austenite present above upper critical temperature. So heat the samples above upper critical temperature, that is in the austenitic region. Hold it there for sufficient time so that all the uniform austenite or homogeneous austenite you will get, that is around 870 degrees centigrade, and let us wait there for 2 hours. So this soaking time is important, because in this soaking time, due to this soaking time, you will get homogeneous austenite. Otherwise, if you are not holding for prolonged time, you are just hitting up to austenitic region, you are not holding there, and suddenly you are pulling back. In that case, you will get the austenite, but that austenite will be chemical gradient austenite. Means the chemistry of the austenite is changing from point to point, like in case of pore structure. Okay, so in order to get homogeneous distribution of carbon or homogeneous austenite, we need to hold it there for some time. So as we know here, the heat treatments, so annealing, so hold it there, all the samples in the austenitic region, and if you are looking for slow cooling, you are cooling the sample in the furnace itself. Do not open the door of the furnace, cool the samples in the furnace itself. Means we are trying to achieve the equilibrium rate of cooling. In that case, you will get coarse perlite, which is very ductile. Then some samples you are cooling in the air. In that case, you will get fine perlite, that is strong and ductile. Some samples you are quenched in the oil or water. In that case, you will get martensite. You will get the good hardness and that structure is brittle. So martensite, it is a non-equilibrium phase. Remember that martensite was not present in iron carbon diagram. It is a non-equilibrium phase. It is a non-formed due to non-equilibrium cooling. And suppose you hold the sample in the furnace itself in between 300 to 400 degrees centigrade. In that case, you will get one more phase, that is bainite. It is hard as well as tough. So bainite is a dream phase for all the heat treaters because it has properties of strong fine perlite as well as martensite. So bainite is a dream phase for all the heat treaters. So this is the basis of heat treatment is the iron carbon phase diagram that we have already discussed that. But the important part here, we are only discussing about this part. Okay. So we are discussing about this part. We are not going to cross 2% because we are discussing only steel part. More than 2% cast iron starts. Okay. So this region is very important as far as our heat treatment part is concerned. We discussed in the previous module how austenite transforms into perlite, but here we'll discuss how perlite transforms into austenite during heating. You just look at this. You just look at this diagram and read the statements which are provided there. So as you can see in this particular slide, so let us consider this is our austenite phase. So what happens by gradual during heating? Let us consider it is a eutectoid steel which contains 0.8% carbon. So during heating, what happens? So first, as we know, austenite is a high rich phase, high rich carbon percentage phase. So first cementite layer forms. So first cementite layer forms, as you can see it here. So cementite takes all the carbon from the surrounding austenite, and these adjacent layers of cementite is now poor in carbon percentage. So that's why ferrite forms. So by gradual dissolution of carbon of cementite into gamma ion, so primary austenite grains are formed. So here first austenite grains are formed. So austenite grains just close to cementite is now grow at the expense of ferrite. We can see here cementite ferrite is nothing but perlite. But during heating, what happens? So this cementite loses the carbon, and carbon enriched layer forms close to cementite layer, and that's why austenite forms. Now this austenite is growing in size by compensating ferritic region. So the growth rate of austenite formation is higher than the rate of dissolution of cementite into austenite. Because austenitic grain takes place because of transformation of alpha ion to gamma ion. And the diffusion of carbon plays very important role from austenite to ferritic conversion. So you can see it here in the last picture. You have here, second last picture, you have here all the austenite, but this was the original cementite part or cementite region where cementite was formed. If you not hold the sample in the austenitic region for prolonged time, cementite, original cementite was there, in that particular region you will get high percentage of carbon, and where original ferrite was there, you will get low percentage of carbon. So means chemical gradient exists within the austenite. So in order to reduce, or in order to avoid, or in order to dissolve this chemical gradient, we need to hold the sample in the austenitic region, and you will get homogeneous austenite. So from this particular discussion, we can we can draw one conclusion, is that in case of iron carbon diagram, let us assume that you can assume that here in case of iron carbon diagram, if you heat the sample, up to austenitic region somewhere here, as far as our austenite phase diagram is concerned, it says that we have here austenite. We have here austenite. Let us consider 0.7% steel. If you are hitting this steel somewhere here, we have austenite. But it doesn't say it is a homogeneous austenite or non-homogeneous austenite. It says austenite is there. But what we discussed in so far, you will get homogeneous austenite only when you hold the sample for prolonged time. So time axis is not available in case of iron carbon diagram. Remember that time axis is not available in iron carbon diagram. So heat treatment cycle will be, if you draw the heat treatment cycle, so hold the sample. So this is our 727 degree centigrade line. Okay, so hold the sample above austenitic region for prolonged time, then you can go for cooling. So this time axis, so this axis is the time which is not available in iron carbon diagram. So iron carbon says heat the samples above austenitic region, you will get austenite. But for how much time? You have to hold it there, then only you will get homogeneous austenite. So in case of heat treatment, we are looking at homogeneous austenite. Remember that. Time axis is not available in iron carbon diagram. Now let us come to the one more virtual experiment. Let us take eutectoid steel, that is 0.8% carbon steel. And this steel we have heated up to austenitic region. Now for every heat treatment, the parent phase is austenite. So we are heating the steel sample up to austenitic region. Hold it there for prolonged time because we are looking at homogeneous austenite. So hold it there for prolonged time. Then we have number of samples available. Around 5-10 samples are there in the furnace 1. So the temperature of furnace 2 is less than 723 or 727 degrees centigrade, that is lower critical temperature line. And temperature of furnace 3 is nothing but it is a salt bath or brine solution. So all the samples we have heated we have kept into the furnace 1, and we have heated up to the austenitic region, that is more than 727 degrees centigrade. That is eutectoid steel. As we know, in case of eutectoid, more than 727, we have fully austenitic phase. So we have heated all the sample up to austenitic region, hold it there for some time so that you will get homogeneous austenite. Then transfer one sample directly into the furnace 3 without wasting any time. The second sample, so the first sample directly transfer into the furnace 3 without wasting any time. So means the time of aging of first sample into the furnace 2 was 0. So that's why we write T1 equals to 0, because we have not hold the sample in the furnace 2. So directly we have quenched the sample into the furnace 3. So time 0. In that case, so go for micro examination of the sample, go for polishing and etching, and by using optical microscope you can see which is the phase present in there, and by looking at the phase you can say it is a, we determine that 100% martensite or not 100%, I would say theoretically 100% martensite is present in the first sample. Okay. Now next, remember that temperature of furnace 2 is around 727 degrees centigrade and temperature of furnace 1 more than 727. Now the second sample we will take it from furnace 1. Let us hold the sample into the furnace 2 for 1 minute. So we are holding the sample into the furnace 2 for, let us say, 1 minute. Then we are quenching the sample into the furnace 3. So now, if you look at the microstructure of the second sample, you will get some perlite plus martensite. In this case, you will get 20% perlite and 80% martensite. Let us take the third sample from furnace 1. Now we will hold the sample in the furnace 2 for 2 minutes. Then quench in the sample furnace 3. So here now percentage of perlite is 40% and percentage of martensite is 60%. So like that, we will increase the holding time of the sample into the furnace 2. And in the final sample, we obtain 100% perlite into the furnace, into the sample. So what we have done? We have increased the holding time of all the sample starting from 0 to n. And finally, we have obtained 100% perlite microstructure into the given samples. Now let us take one more set of samples. Now we will decrease this 727 degrees centigrade to, let us, 700 degrees centigrade. So the temperature initially was 727 or 723. Now let us come to 700 degrees centigrade. We have decreased the temperature. The rest of the things are same. Furnace 1 temperature, furnace 3 same. Again we will carry out the same experiment. So slowly we are increasing the time of holding of all the sample into the furnace 2. So by using this experiment, by using this virtual experiment, what we have obtained is, for this temperature, corresponding temperature, for example T1, we have obtained time required for transformation, starting from 100% martensite to 100% perlite. That is at 727 or 723 degrees centigrade. Similarly, for 700 degrees centigrade, we will determine the time of transformation from martensite to perlite. Again, carry out experiment for next T3 and find out time required for transformation. That is from martensite to perlite. By using this experiment, we have determined for each test temperature, what is the amount of time required for complete transformation from martensite to perlite. Now we can construct, by using this series of isothermal curves. What I am calling isothermal means at constant temperature we have obtained some data. So we will get series of isothermal curves. And by using this series of isothermal curves, you can see it here. So first is austenite transform. So vertical axis is austenite transform and horizontal axis is time. You can see it here. So for first temperature, the time of transformation starts from here and it will end here. Means beyond this time, so 0 to up to this particular path, there is no transformation available. So austenite has not transformed to any other phase. So this period we call incubation period. So this period we call incubation period. So this period is very important. There is no transformation of austenite to any other phase. So incubation period. So from this point onward, transformation starts. And at this point, a transformation ends. Means 0% to 100% austenite is transformed. So at this point, austenite transformation start, and at this point, austenite transformation has ended. So this is the time required for transformation of austenite to perlite or austenite to martensite, whatever it may be. Now in the second experiment, let us take T2 now. You can see it here, T2 line. So from this temperature onwards, time onwards, austenite has transformation starts and it has ended here. So this period we call incubation period. Similarly for T3, so the incubation period. Now T4, incubation period. So you can see it here, T1, T2, T3, T4. So temperature T2 is less than T1, T3 is less than T2, T4 is less than T3, T5 is less than T4. Like that, temperature we are continuously decreasing. So as temperature decreasing, incubation period also decreases. But after one point, you can see it here, T5, again incubation period has increased. Again for T6, incubation period has increased. Why incubation period has increased, I will explain later on. But you can see it here, T1 is greater than T2 and T3. Now by using this series of isothermal curves, we can plot one graph here. So horizontal axis becomes time and vertical axis becomes temperature. So for this temperature, T1, you can find out this time at which transformation starts. So this is the time at which transformation starts. And this is the time at which transformation ends. So this is the time. Similarly for T2, so this is the curve of T2. At this point transformation starts and at this point transformation has ended. Similarly for T3, so this time transformation has started and at this point transformation has ended. Similarly for T4, so T4 has the lowest incubation period, you can see it here. Now less than T4, that is T5, transformation incubation period has now again increased. So T5, T6. So you can join all the points, and when you join all these points, you can obtain one curve. And this curve you can see, you can say this curve as time, temperature, transformation. So this curve we call T curve. So time, temperature, transformation. So this curve we call as a time, temperature, transformation curve. And this is the TTT curve for an eutectoid steel, means the steel which contains 0.8% carbon. So this curve is also called C curve because it looks like C. So we call this curve as also C curve. And this is the nose of a C curve. So this part we call nose of a C curve. So this curve indicates, so this line, this indicates start of transformation and this is end of transformation line. So start of transformation and end of transformation. And by experimental data, we obtain that so time required for perlitic transformation. So initially for 0 seconds, as we know that in the previous study here, so for each test temperature, we have determined the time required for transformation of austenite from to martensite to perlite. So for suppose you have heated the sample up to the austenitic region somewhere here, and suppose you have quenched it very drastically without less than 0 seconds or almost 0 seconds. In that case, you will get martensite. You can see it here. So martensite. So here also you will get martensite. Here also you will get martensite. So the time, but when you just touch this here also you will get martensite. Means by using series of experiments, we have constructed this curve, and you can find out the time of quenching. Below that only you will get martensite, like that. So this, by using series of isothermal curves, we have obtained this, we have constructed this diagram, and these are nothing but continuous. We are quenching the sample, holding it there in the furnace 2, then you are quenching into the furnace 3. So at this time you can see it here. So this particular portion, now regarding this incubation period, so T1, T2, T3, you can see initially incubation period was high, now slowly decrease, and more than T5, less than T4 for temperature, again it has incubation period has increased, because we know that close to 200 degrees centigrade carbon diffusion starts. So means for diffusion we require temperature. So less than T4, temperature value is very low. So that's why diffusion rate is very low. In that case, due to low temperature, the diffusion rate has decreased, and due to that, diffusion rate has decreased. So that's why incubation period has also increased. But above that, we have high temperature, but the phase which is present here was the heterogeneous austenite, that is unstable austenite, and that has to be homogenized. So that's why the incubation period initially was high. Why incubation period for T1 is high? Because time required for perlite to perlite to austenite transformation, as far as our iron carbon diagram is concerned, 0 time required for perlite to austenite for eutectoid steel. But practically, we require some time for perlite to austenitic transformation, and this time is the incubation period. So that's why here initially we have high incubation period, and slowly it now decreasing, and beyond T4, less than T4, incubation period again increased. It is due to the fact that temperature increases, diffusion rate increases, but here diffusion rate has decreased, so that's why incubation period has increased.